Okay, good morning everyone. So, welcome back to this course on solid mechanics. This is Vignesh, and I'll be talking about a few problems today based on stresses and strain that we have seen in the earlier classes. So, if you remember, we talked about the different types of forces in the last class, and before that, the relationship between stress and strain. If you remember, stress is the ratio between force and area. Stress is again, if you want to define it perfectly, it is the resistance to the external loading. And I'll just write resistance because that's the key word over here, resistance to the external loading, which is P. And the load is applied on this particular area. For example, if we take a bar like this, if the bar is having a cross section which looks like this, and if the load is being applied in this particular cross section, if I draw lines which represents the area resisting the cross section, this is it. So this particular area, if for example this is B and this is H, that area which is taking up the particular load should be utilized for the calculation of A. So that's very important. Once we go into the problem, it will be very easy for you to understand. And apart from that, we have also learned about strain, which is change in length by original length. So these two things are very, very important. So one more graph which we will talk about, and then we will move to the problems, is a stress strain curve. I will use a stress strain curve for a mild steel bar. Right? If I draw, I'll just take an x-axis, let's do some different one over here, and x-axis over here. So if I draw stress over here and strain over here, the graph will look something like this. It will start to increase, and at a point it will come down slowly and then gradually increase, and then it will break. Now there are a few points which we need to note down. The first one, I'll just tell very important points. This is point number A, this is point number B, this is C, this is D, and this is E. Right? So I will also talk about one more point, which is A dash, which is a very important point which I will leave you to understand what that means. So if you take A, that is called an elastic limit or elastic point, whichever you want to use. So within this elastic limit, the material can come back to its original position. When you think about it like a rubber band, when you pull a rubber band till a certain point, it won't break, and if you leave the force or if you leave the rubber band again, it will come back to its original position. That's elastic limit. That is well within the elastic limit, and that is why it's called this point. And for a mild steel bar, this point is very, very important. Point number A. Point number A dash, I will leave you to understand what this is. This is like a homework. Limit of proportionality, right? So I will leave you guys to understand what that means, because I cannot tell every single thing for you inside a 10-minute video. So I'll leave you guys to see what A dash means. Let's talk about the other points, B and C. These are again very important points. These are called upper and lower yield points. Okay. Now what is an yield point? Suppose if you have well, let's take the 5-star again. If you start pulling that 5-star, it won't come as soon as possible. It will elongate, or it will start to elongate at the point. That point is called yielding point or yield point. This moment where the material starts to elongate, it starts at that particular point, and that point where it starts to elongate is called a yield point. So these 2 points, upper yield is B, upper yield point, and lower yield point is C. So these 2 points are very, very important, and they will tell you a lot about the characteristic strength of that material. If we talk about Fe250, this number that you see over here is the yield point. Okay, so 250 Newton per mm squared is the yield point for that particular material. Okay, so yield points is the point where it starts to elongate. It starts. Now coming to D, this is the maximum stress that the material can take, hence it is called ultimate stress. And finally E is the breaking point, right? So I'll just rewrite it again. A is the elastic point where the material can come back to its original position after the load is removed. A dash is the homework which I was talking about, limit of proportionality. It's very important, so please do note it down. B and C are upper and lower yield points. So yield points are the points where the material starts to elongate. D is the ultimate stress or ultimate load, and finally E is the breaking point or breaking stress. Okay, right, so these are the points which are very important when it comes to a stress strain curve. And with that I will also take another rule which we obviously will be using in this course called Hooke's law. And if I go back to this point, and if I just take this portion alone, this particular portion within the elastic limit, and if I draw this, and if I draw a stress strain curve, I'll just use a line because that will be easier for us. This is it, and then you have a line. So if I draw the stress and strain over here, this is stress and this is strain, you can see it is varying very linearly. The variation is linear. Okay, that's a very important thing. And Hooke's law states that within the elastic limit, and that's a very important point, within the elastic limit, you should underline that, stress is proportional to strain. Okay, and why should we use such a thing? Why should we use a material within the elastic limit? This is easier for the calculation purposes. When you go beyond it, it's called plastic analysis, which will be not proportional, and that is why we are using it like this. Inside the elastic limit it is very easy because it's a linear variation and not a non-linear variation, which can lead to a lot of complicated calculations. So if I take this sigma is proportional to C or strain, if I want to remove this proportionality constant, I'll just use this. I'll use this E into strain. So if I rewrite this again, E is equal to stress by strain. This is called Young's modulus. Okay, and the unit will be Newton per mm squared, because strain does not have any unit, stress has a unit of Newton per mm squared, right? So these are the few things which I wanted to talk about when it comes to a stress strain curve. And we have derived an equation, not an equation, we didn't derive it, but we got a formula for Young's modulus, or you can also call it as modulus of elasticity. So that is stress by strain. Okay, so if there is any doubts, do let me know in the comment section. I'll see you guys in the next video. Thank you.